ideal operation. And in classic op-amp circuit analysis, we assume ideal operation in favor of simplicity. So while we can go through that whole analysis that we were looking at on the last page, it's easier for us to just make some of these assumptions that we are operating under the ideal conditions, so that we don't have to do all the algebra involved in solving two equations at once, and so on. Because there's only a very small increase in accuracy when you do so. So if you do need the accuracy, and you do need to really see the full picture, you can use today's free Spice software, which you can download for free. A popular one is LT Spice, which is produced by Linear Technologies, and you can use that software to paint a more accurate picture of how your op-amp circuit is working, because that accounts for all of those real characteristics you're looking at. However, when you're trying to do pencil and paper op-amp circuit analysis, 99.999% of the time, you assume ideal operation, and that's what we're going to assume from now on in this video. So since we're talking about ideal op-amps from here on out, we should probably go over the characteristics of an ideal op-amp. Now, this is going to be an incomplete list. There are more characteristics, but for now, these three will get us off on the right foot. An ideal op-amp has infinite open loop gain, which was just what we were talking about a few seconds ago. It means that if we look over at this high-level model of an op-amp, that the value of AV, which is connected to this dependent source, so we brought back the dependent sources from this, the value of AV equals infinity. And we'll go over just what that means in a second. I'm just going to list them for now. The second characteristic is infinite input resistance, so that means that the value of RI right here is infinite, so the resistance that both inputs effectively see is infinity. And the last characteristic is zero output resistance, which means the value of RO is zero. I'm not going to talk more about zero output resistance, so in a nutshell, what it means is that the op-amp can source or sink infinite current, because there's no resistance. If there was a resistance there other than zero, this would mean that the op-amp would dissipate power in that resistor. So in practical terms, you have to worry about thermal dissipation and making sure that your op-amp does not overheat and go up in smoke. So now we'll see what these characteristics imply, and namely the first two here. As they stand, these characteristics don't really make our circuit analysis lives any easier. However, if we can draw some conclusions from them, we might be able to help ourselves out. So for our first characteristic of an ideal op-amp, that's infinite open loop gain. And now we'll bring up our graph, our output graph before, and see how it's changed with AV now equal to infinity. Right away, you notice that the op-amp is now almost always operating in saturation at the positive or negative supply voltage, except for at a single point here, where the difference between the two inputs is equal to zero. It also corresponds to an output equal to 0 volts. Now that's interesting because we are interested in amplification, so we want to operate in the linear region by definition. So what is the only way that we can operate in the linear region? Well, the only way we can operate in the linear region is if we operate at this single point right here. So if AV is infinite, which it is in this case, then the only way to stay in the linear region is if V plus minus V minus is equal to 0. And that's to say that V plus must be equal to V minus. And so that's our first conclusion that we can make from our ideal op-amp characteristics. Next up, what does it mean to have infinite input resistance? Well, first let's think about why we might want this. An amplifier should be, quote-unquote, invisible to whatever sources are connected to its inputs. So that means if we have something like a sensor that would be represented by a voltage source in series with a resistor, this would be a Thevenin source, in this case, if you remember. And that sensor is connected to an op-amp with an input resistance here. Then the input resistance of the op-amp and the series resistance of the sensor form a voltage divider. Now, if the input resistance of the op-amp, Ri right here, is infinite, then all the voltage produced by this voltage source here appears at the terminal V plus. That's good because we want all the voltage that the sensor has to offer. But if the op-amp's input resistance is anything but infinity, it's anything lower than infinity, then a current flows into the inputs, and voltage is dropped across the series resistance here. So not all the voltage appears at the terminal V plus. Now, an ideal op-amp has infinite input resistance, so no current flows into the op-amp's inputs. So that means that I plus and I minus must both be equal to 0 if we have an infinite input resistance. And that's conclusion number 2. This is how we just learned, but let's formally state the two golden rules of op-amps. The first rule is that the output attempts to do whatever is necessary to make the voltage difference between inputs 0. Now this is only true when you are using an op-amp circuit with feedback, because there's no way for the output to change within the input unless it is in some way connected back to the input. The second rule is that the inputs draw no current, which is exactly what we just said in the previous slide with I plus and I minus equal to 0. And with these two rules, we are now ready to solve any ideal op-amp circuit. In fact, I would start this video from this slide and then an excellent op-amp circuit analyzer. However, I wanted to convince you that these rules were grounded in something and have some sort of reasoning instead of just throwing them at you and telling you to take them for granted. So I hope that you appreciate that, and if you didn't, well, please don't hate me. I'm sorry. Now we're going through some of the most useful and popular op-amp configurations, and this is actually going to be the easy part because it's just a matter of applying the two rules we just developed and using some basic circuit analysis skills. So for this example, we're asked, what is the closed loop gain, VO over VS? And closed loop gain is just a term used when we're talking about op-amp circuits with closed feedback loops, which this one does and all our subsequent examples will. So let's restart. Well, let's look at the non-inverting input. At the non-inverting input, we have a voltage V plus, and we see that the non-inverting input is connected back to the voltage source with voltage VS. So that means that V plus equals VS. And we also know that an op-amp does whatever it takes to make its two input voltages the same. That is, to make V plus equals V minus. And so if V plus equals VS, then it follows that V minus also equals VS. So that's our first fact, that V minus equals V plus, which all equals VS. Now we should notice that V minus, the voltage at the inverting input, is also the output voltage of a voltage divider consisting of RF and RG. Remember that a voltage divider produces a voltage which is a fraction of its input voltage. And in this case, the input voltage to our voltage divider is actually VO, the output of our op-amp. And VO is fed to the input of the divider, the top of the divider here. And the output of the divider is fed to the inverting input of the op-amp. Now by changing the values of these two resistors, we change the amount of voltage that appears across RG. So we change the fraction of the output that is delivered to the inverting input, and that is that we change the value of theta, bringing back theta, the feedback factor from before. Now, just for clarity's sake, this voltage divider, it makes up what's known as a feedback network, which is a general term to describe a group of components in the feedback loop of a circuit like this. Now, there's a couple ways of looking at this, but the only way the output of the divider, which has a voltage V minus, can equal Vs is if the input to the divider, which has a voltage Vo, is a voltage larger than Vs. Vs is voltage set in stone, is the voltage of an independent source. So why does it make sense that Vo has to be greater than Vs? Well, remember that the output of the voltage divider is a voltage smaller than its input voltage, and the input of the voltage of this divider is Vo. Then it follows that V minus is a voltage smaller than Vo, or that Vo is greater than V minus. And if V minus and Vs are the same, then it also follows that Vo is greater than Vs. And so that is amplification, and that's what we're looking for this whole time. So we're asked to find the closed loop gain of the circuit. And since there's no value associated with Vs, RG, or RF in this case, then we're really just deriving the general gain equation of the circuit. And that means that if we're presented an op-amp circuit which looks just like this, then instead of going through all the mathematical algebraic legwork every time, we can just use the general form we're about to derive and just plug in our resistor values. And this configuration, as you may have guessed from the huge title on top, is called the non-inverting amplifier, or the non-inverting configuration, and it has its own gain equation associated with it. So let's figure out what that equation is. So we'll start off with the fact that we know before that V minus equals V plus equals Vs. And we also know that the voltage V minus is equal to the voltage dictated by the voltage divider equation, which is in yellow right here. And it says that the input voltage is multiplied by this fraction, which is RG over RG plus RF, and that gives you the output voltage of the divider, which is the voltage V minus. So great. And now that fractional part of the voltage divider equation is actually theta. Interesting. So now we can solve for VO over Vs, and we can find the closed loop gain equation. And so that is VO over Vs equals RG plus RF over RG. But we can make that look a little neater, and we can simplify that to 1 plus RF over RG. So every time we see an op-amp circuit configured in this way, with resistors here and a voltage source connected here, instead of going through all this crazy math, we just remember this equation, VO over Vs equals 1 plus RF over RG, and just plug in our values for RF and RG. Now tell us how much our op-amp circuit will multiply our input by. So to find our output voltage, we simply multiply our gain here by our input voltage. That's very simple. Now, one thing to think about, and we'll compare to the configurations in the subsequent slides, but we have to have a minimum gain of 1. We cannot go below a gain of 1 in this configuration because of this one term here. Just something to think about, and we'll compare to the future configurations we're going to go through. This next configuration is called the buffer, or what is sometimes called voltage follower. And the buffer is really just a non-inverting amplifier without a feedback resistor network. And so that's realized as just shorting the output directly to the inverting input. Now this configuration, in order to keep the two inputs the same, keep V minus equal V plus according to our golden rule, the op-amp must produce a voltage VO, which is exactly equal to Vs. Because if V plus equal to Vs, and V minus has to also equal Vs, and the only way that happens is if the op-amp produces an output VO, which equals Vs, which is set back to that inverting input. So that's to say that its gain is 1. And now, that doesn't make sense because number 1, the amplifier signals make it bigger. What's the point? So it makes sense of why we would ever want this in the real world. Let's get back to the first video in this series and perhaps our existing circuit analysis knowledge. Now let's think about the loaded voltage divider. That is a voltage divider with a load that has across its output. So in this case, when we attach a load RL across the output of the divider, we actually change the very voltage at the output because the load draws current from the divider and alters the entire voltage divider equation. Can you think of a circuit which will not alter the output voltage of the divider, yet can still drive the load RL? And here's a really, really big hint for you. The input resistance of a buffer flash device is practically infinite, and the output resistance is ideally 0. So here's just what I was really trying to hint at. Basically what we've done here is we've detached the load resistor RL from the voltage divider, and in between we've inserted an op-amp buffer. So how does this help us? Well, the golden rules tell us that the inputs of an op-amp draw no current. So if you attach the output of a voltage divider to the input of an op-amp, no current flows out of the output of the divider. And this means, as we know, that if we don't draw any current from the divider, that the voltage at the output of the divider does not deviate from the voltage we expect using the voltage divider equation. Thus, the output voltage of the divider will not change when an op-amp buffer is attached. Basically, what's happening here is the op-amp is observing its input voltage, which is in this case the output of the divider, and replicating that voltage on its output. So it's really just making a copy of the input and pasting it on the output. And now, the real thing about an ideal op-amp is that it has ideally 0 output resistance, so that means that it can supply any amount of current to the load, and it'll have no problem with that. In this case, the voltage divider circuit and the load are isolated from each other. They don't use the same electrons, if you will, because the op-amp in the middle is acting as a middleman, playing telephone with the input and the output, hence the name buffer is used. Next up is the inverting amplifier, and it looks like this diagram over here on the right. With an inverting amplifier, we now connect the input to the inverting terminal, and you'll notice that the non-inverting terminal is connected to ground. So again, we're asked, what is the closed loop gain VO over Vs for this configuration? So if V minus has to equal V plus by our golden rule, then V minus, the voltage at the inverting input, has to sit at 0 volts because V plus is attached to ground, and we know that ground is 0 volts. Also, recall that the inputs of an op-amp do not draw any current, so no current should enter the inverting or the non-inverting terminal. Now, let's call the node which connects RI, RF, and the inverting input, let's call that node 1. And now we'll perform the Kirchhoff's current law or KCL analysis at that node. We'll assume that the currents associated with these two resistors, that is Ri and Rf, are flowing into the node, and that the current In is flowing out of the node. And that might raise a flag in your head, In, because you know that no currents flow into an op amp, and you're right, but we're going to keep that there for technicality's sake. So our KCL equation is going to be II plus IF minus In, all equals 0. Now, we want these currents in terms of voltages and resistances, because we want to find the closed loop voltage gain, VO over Vs. So how can we define the current through, say, Ri? Well, we know that the current through resistors, just the difference in voltage across it divided by its resistance. So what's the difference in voltage across Ri? Well, it's going to be Vs minus 0. Here's the minus sitting at 0 over Ri. So in this case, it's just going to be Vs over Ri. And so that's the first term of our nodal analysis equation. We now call this nodal analysis when we're dealing with voltages and resistances. So that's our first term. That's going to be Vs over Ri. So now how do you define the current through Rf? Well, we already see it on the screen, but it's going to be the voltage at the top of the resistor, which is VO, minus voltage at the bottom, which is 0 over the resistance, which is Rf. As you see here, just VO over Rf. And put out that current In, which points into the op-amp's inverting terminal. Well, I probably shouldn't have you put that there, because we know that no current flows into an op-amp. So that's 0, and that goes away. So you set that all equals 0, and we get our final nodal analysis equation here. And now it's just a matter of rearranging to solve for the closed loop gain, which is actually going to be minus Rf over Ri, and that is the closed loop gain for an inverting amplifier. Now, interestingly, in this configuration, we see that the voltage on the output is inverted. Let's say that if we were to apply a positive voltage to the input, that is if Vs was positive, then we would get a negative voltage on the output. That would mean that VO is negative relative to ground. Also, whereas in the non-inverting amplifier that we looked at a couple slides ago, we noticed that we could not amplify by a value less than 1. The inverting amplifier can. That means that the inverting amplifier actually has amplifier, which is something that increases. And one final thing to note is that the input resistance of an inverting amplifier is effectively the value of the resistor Ri. Now, the internal resistance of the op-amp is still infinite, as we said, but in this configuration, your source, so in this case that's Vs, your source sees the value of the resistor Ri as the input resistance of the amplifier. So I just mentioned that because it's a common trap for young players, because if you use too low a value of resistance for Ri, then you can start to draw some serious current from your source, and you can start to see some really wacky things, so just keep that in mind. Next up is the summing amplifier, and at heart the summing amplifier is just an inverting amplifier configured to produce the sum of its input voltages. So I say it's just an inverting amplifier at heart because if you look at the diagram, the right half of the diagram is identical to the standard inverting configuration, and the left side of the diagram is actually really similar too. We just added on 2 more inputs. So you know what it does? It finds the sum of the input voltages. So how do we get to that conclusion? Well, we're going to start off by doing a KCL analysis on this node right here on the inverting input, just as we did before. And of course there's going to be 5 associated currents with this node, and they are I1, I2, and I3, and those are the input currents, the feedback current IF, and the op-amp input current IN. And we know IN doesn't really exist, but we're just going to keep it there for now. And so what does the KCL equation look like? Well, it's going to be I1 plus I2 plus I3 plus IF minus IN equals 0. And the KCL constant convention we use for writing these KCL equations is if a current is entering a node, it is a positive current, and if the current is leaving a node, it is a negative current. So just to find that we're really interested in voltages, input and output voltages, and how they relate. So we define the voltage-current relationship for all these currents. So how do we do that? Well, let's look at current I1, which goes through resistor R1. How do you define the current through a resistor? Well, it's the voltage across that resistor over its resistance. So what's the voltage across R1? Well, it's going to be V1 minus 0, because this whole node is sitting at 0 volts because the non-inverting input is attached to ground. So that's just going to be V1 over R1. And that's the first term in our nodal analysis equation here, V1 over R1. And so the same thing follows for the next 2 inputs. For the current I2, which passes through R2, is just going to be V2 minus 0 over R2. And that's just going to be V2 over R2. And for the third current I3, it's going to be V3 minus 0 over R3. And that's what you see on the third and final input term there. And for the feedback resistor RF, the current that goes through that, which is IF, is the same. It's defined the same as it was in the inverting amplifier, and that's going to be VO over RF. And we move to the other side of the equation because we want to solve for VO, and so of course it becomes negative now. So now we have our input voltages and our output voltage in the same equation, so now we can solve for VO. So let's do that. And so here is what the most general equation of a summing amplifier looks like. This could be our answer, but we're going to do one little simplification after this. But looking at this equation, what does it tell us about how this summing amplifier works? Well, we see that we can adjust how important each one of our inputs is to the final output voltage. And how can we do that? Well, you see that there's a constant RF term in all of the, that applies to each of the input voltages, but each input voltage has its own input resistance, and those are R1, R2, and R3. So we can individually adjust the weight or the importance of each input to the final output voltage, VO. So if we make R1 really big, then we quote-unquote reduce the importance of V1 because the denominator of this term right here gets bigger, so this whole term gets smaller. And if we do the inverse, so we make R1 really small, then we make the term, the V1 term here bigger, so we can adjust how much impact each input has on the final output. Now, what if R1, R2, and R3 are all the same, which we might want to do in some cases? So in that case, if all input resistances are equal, then the output voltage VO is just going to be negative RF over RI, and RI is just a general term for those input resistances, which are now all going to be the same. And then that multiplied by the arithmetic sum of all the input voltages. And we'll note that we go all the way up to Vn, because we can have as many inputs as we want. We just have to add them on. But I just showed 3 here because I thought it illustrated the point. And so yeah, that is our final So, we know find the difference. Well, how does it do it? Well, let's find out. So first off, as always, we know that the inverting and non-inverting input voltages are going to be the same. That is that E minus equals E plus. We also know that the voltage at the non-inverting input here is dictated by the voltage divider equation, because E plus is actually the output voltage of a voltage divider consisting of R1 and R2. And we're trying to find the voltage across R2. So we can say that V plus will equal V minus equals V2 times R2 over R1 plus R2. Okay, so let's focus on voltage for a second, and now let's look at the inverting terminal. And once again, let's perform a KCL analysis at the inverting terminal here. What are the currents associated with this node? Well, we have two currents. We have I1 and IF. And we've left out that I in current, that input current to the op amp, and I think by now we know that no current flows into the inputs of an op amp. So our KCL equation is simply I1 plus IF equals 0. And once again, we're interested in voltages, not currents. So let's look at these currents in terms of voltages and resistances. So how do you do that? Well, let's start with I1. How do you define the current I1, which goes through the resistance R1? Well, it's going to be the voltage across that resistor divided by R1, as per Ohm's law. But the voltage V minus here is no longer 0 because V plus is no longer connected directly to ground. So we're just going to call the voltage here, we're going to call it V minus here as well. That's what it is. So for the first current I1, the current is defined as V1 minus V minus over the resistance R1. And very similarly for the current IF, current is defined as VO minus V minus over R2. And we move that to the other side of the equation, which makes it negative. So now we can start the process of solving for VO, which is what we're interested in. And so that's the one of algebra and rearranging. And eventually we'll get to an equation which looks like this. And now we can do some substituting of some information we already know. And so we have V minus by itself here. But what we know also equals V minus, well, look at the top here. We know that V minus equals V2 times R2 over R1 plus R2. So what we're going to do is we're going to substitute that in to our equation. So now we have VO as a function of V2 and V1, which is exactly what we want. And another great thing is you'll notice that we have an R1 plus R2 term on the bottom here and an R1 plus R2 term on the top here. And that means that we can cancel those two right out. Before we go any further, the reason that happens is because we've made R1 and R2 occur twice in our diagram. As you can see, these two resistors are the same value when we do that, so that this cancellation can happen. And of course, we've also made these two values, R2 values, the same for that same exact reason. If we didn't do that, this kind of fancy cancellation wouldn't have happened at this point. So great, so now we've canceled that out. Well, if we just do a little more simplification, we see that VO equals V2 times R2 over R1 minus V1 times R2 over R1. So once again, if we do a little more simplification, we get to the final output equation, and that is that VO equals R2 over R1 times the difference between the two inputs, and that's V2 minus V1. So this is awesome because what happens here is we get a difference between those two input voltages, V1 and V2, and then we apply some amount of amplification to that signal. So if we have a really low level signal, say from a sensor, we would want to use a difference amplifier, and we want to increase the level of that signal, and we do that by adjusting the value of R2 and R1 accordingly. Now the word on the top of your screen might be scare to you if you haven't taken calculus, or maybe it's even more scary if you have taken calculus. But before we actually scare ourselves, let's consider an example. So say we have a bucket and a faucet, which is, by the way, what's here on the left. And if water comes out of that faucet at a constant rate, we expect the bucket to be filled at a constant rate too. And that would look something like this. So a time for the faucet is also that before we turn it on and after we turn it off, there's no increase in the volume filled in the bucket, which is what's on the y-axis here. And when the faucet is on, you see that the volume filled increases at a steady rate. And that rate is dictated by the flow rate, which is dV over dt, which is how much the volume changes in an instant of time. So the continuous accumulation in the bucket during the time when the faucet is on, which is caused by a constant flow of water, is basically the act of integration. So integration is an accumulation over time. And on the next page, there's a circuit with a new component called a capacitor. And we're going to see that our capacitor is a lot like our bucket of water. And if you don't understand any or all of that, or this, that's okay, because you can still do the derivation. But I just wanted to throw this in, so that there is at least some level of intuition, not just straight math. So how is a bucket filled with water a lot like a capacitor? Well, for starters, we had a flow rate, which was how much water is moved into the bucket in an instant of time. And in a very similar fashion, for a capacitor, current is how much electric charge is moved into a capacitor in an instant of time. So with our example here, we're trying to move water, and with a capacitor, we're trying to move electric charge into the capacitor. So the capacitor is our storage device. And the volume filled in our bucket is a lot like voltage. So if we, in a capacitor, moving charge into a capacitor increases the voltage. The more charge you put into a capacitor, the bigger the voltage. Just like the more water you put into a bucket, the greater its volume filled is. And last but not least, the size of the bucket is like the capacitance, which is how you rate the capacitor, or those one of the measures. So with a small bucket, we can fill the bucket very quickly, but also it's very quick to empty the bucket too. And same thing for a capacitor. The larger the capacitance, the more charge it takes to fill that capacitor up. Alright, so you know all that. Let's move on to the next part, which is actually applying this to an op-amp circuit. Now let's apply the water bucket analogy to this circuit, and the circuit is called an op-amp integrator. And the new component we're talking about is a capacitor, and that has this circuit symbol with two parallel plates, and has a capacitance value of CF. If we force a constant current, ICF, through capacitor CF, then a voltage will be produced across it that increases at a constant rate. So you can think of a constant flow rate of water causing a bucket to fill at a set rate. And for a capacitor, a constant current or constant flow of charge into a capacitor causes the capacitor to charge at a set rate, or to change its voltage at a set rate. Same thing. In fact, the capacitor is charged at a rate of ICF over CF. So this makes sense because we know know that the more charge that we dump into the capacitor amount of time that is in current, the faster the capacitor will charge up. We also know that the bigger that capacitor is, or the higher the capacitor's value, the harder it is to charge that capacitor or to change its voltage. So that's why the rate of change of voltage across the capacitor is proportional to the current that's forced into it, and inversely proportional to the value of the capacitance or its size. So we can just rearrange this and we can determine what the value of ICF is, or how we define ICF in terms of the rate of change of voltage and capacitance. And so very simply, ICF we find out is equal to CF in capacitance times the rate of change of the voltage across the capacitor, which is in this case VO, because we see that VO is on one end of the capacitor, and on the other end of the capacitor there's 0 volts, because we are all attached to ground here. Great, so now we've defined ICF, we can perform the nodal analysis, the ACL nodal analysis, out of favorite node, and that is the node attached to the inverting input. So what are the currents associated with that node? They are IS and ICF. And we've said that they're both entering the node, so that makes our KCL equation IS plus ICF equals 0. Now we want to find these currents in terms of voltages, and so how would we do that for IS? Well, we just need to know the voltage across the resistor in which the current is going through, and that's simply going to be DS minus 0, so we're back to that whole 0 case again, because the non-inverting input is connected to ground, so DS minus 0 over RI. And so that's the first term, and the second term is simply what we just found for ICF, which is CF times dVO dt, and we moved it over to the other side of the equation, so of course it's negative. So that's how you define those currents in terms of voltages. And now we're interested in finding the output equation, so what is VO? So we'll solve for first dVO dt, that's equal to that, negative 1 over RI times CF, the quantity there, times DS. And the last little trick, and if you didn't take calculus, this might be magic, but if you did take calculus, you'll know exactly what to do, is we're going to integrate both sides of the equation here, which will make dVO dt become just VO, and the other side of the equation will be the integral of negative 1 over RI CF times DS. But since RI and CF are constants, we can pull them out of the integral, so that our final output equation for this circuit is VO equals negative 1 over RI times CF times the integral of DS for the same time, and of course, don't forget C. So this is cool because we have a real-world circuit that can perform an integrating function, and we can make it produce the exact integral of the signal if we make RI times CF, which is the denominator of this coefficient right here, if we make that equal to 1, then we just have the negative integral of whatever our input signal is. And then if we want to get to the right, a positive integral, how can we do that? Well, all we have to do is look up another stage, or so we call another stage, of an inverting op amp with a gain of negative 1, and we can flip it to the positive integral of our input signal. So yeah, this has a lot of applications, and we'll see one kind of application in the last slide of this entire video. Well, that's about as much theory as I think we should go into, and probably about as much theory as you can expect to know in the course. So we can run some applications. So have you ever wondered how your digital computer or phone plays back analog audio? Because you've always heard people talk about ones and zeros and on and off and binary for a computer, so how could that possibly make an audio signal that is analog? Well, the trick is, it's not really a trick, but what they do is they use digital to analog converters, or DACs for short. So we have a digital audio file. It consists of a sequence of samples, and each of these samples represent one tiny sliver of the total sound clip. So here is what a WAV file might look like. The top part of the WAV file is the chunk description or the format description, and that just kind of tells the computer how to play back the sampled data. And the sampled data is really the meat of the sound file because it contains the actual information, the sound information, to be played back. So 6.4, for instance, is one sample. 6.1 is another sample. 7.4 is another sample. And why am I saying 6.4, 6.1, 7.4? Well, because these are hexadecimal numbers, which means they're base 16, not base 10 as we commonly use. And we're going to convert one of these from base 16 into base 10 and also into binary in just a second. But basically, when you play back this string of sample data at just the right rate, as you reconstruct this information at just the right rate, you're going to hear your favorite song. So just like using a record player, when you play back a record at just the right RPM, you're going to hear your favorite song. Any other speed is not going to sound quite right. And just like in a record, the data is ingrained in little ridges in the vinyl. In a digital sound file, that data is ingrained as you see samples. So we said that all the sample data in this file here is in the form of hexadecimal, base 16, and there's 2 digits for these. So that actually makes these 8-bit samples, so get rid of 8-bit, 16-bit, all that kind of stuff. 8 bits means that we have 8 binary bits to represent one sample. The more bits we have, the more resolution we have, the better the sound file is going to sound when you play it back. So let's look at F9. Let's turn that from a hexadecimal number, so that's base 16, into binary and into decimal. So we can look at one digit at a time. So let's look at the digit 9, base 16. We convert that to decimal, it is also 9. That's convenient. And let's convert that into binary, and if you don't really know how binary works, I'm not going to explain too much. Basically, each one of these digits in a binary number has a different value, just as it does in decimal, except the value is different than decimal. So in binary, we represent the number 9, 1, 0, 0, 1. And we look at the other digit, that is F, and F in base 16 or hexadecimal corresponds to 15 in decimal, and 15 in decimal corresponds to 1, 1, 1, 1 in binary. And so to find the binary equivalent of F9, all you got to do is piece these two together, so 1, 1, 1, 1, and 1, 0, 0, 1. And so in binary, F9 is 1, 1, 1, 1, 1, 0, 0, 1. And in decimal, which might make more sense, the equivalent is 249. And so with an 8-bit number, we can store integer values between 0 and 255. So you see that our number 249 is up on the upper end of the spectrum of the amount of the numbers that we can store in one 8-bit number. Alright, so let's see how we can create a digital to analog inverter with an op amp. The digital analog inverter is traditionally a chip or integrated circuit, but these days you can find digital analog inverters integrated onto other integrated circuits like microcontrollers. So here's a block diagram for a DAC. As you can see, it accepts an input string, a binary string, consisting of V0, V1, V2, and V3, which corresponds to bits 0, 1, 2, and 3. We also have a VREF, which is the reference voltage for the DAC, and we have a voltage out, VO. So how does this translate into an op-amp circuit? Well, it looks like this. And so immediately, right off the bat, probably you're saying, wow, that looks a whole lot like a summing amplifier, and you'd be 100% correct. The only difference here is that we have these switches, which are controlled by the value of the bits in the binary string. So in this case, if we look at bit 0, we notice that the switch is connected to ground or 0 volts. And that must mean that the bit 0 is 0 in the binary string. So there's no current going through this resistor marked by 8 times Ri. On the other hand, if we look at D1, we notice that the switch connects DRF to the resistor labeled 4 times Ri. So that must mean that the bit V1 is a 1. And as you can see, the inputs are either switched on or off depending on what the value of the corresponding bit is. So my next question would probably be, what's up with the different coefficients in front of these resistors? Well, explain that you have to recognize that each position in a binary string, that is each bit in a binary string, so that's V1, V2, V0, V3, all of them, has a different weight associated with it. So in decimal, we know that you have the ones, tens, hundreds, and thousands places, which means that we have a base 10 for each place, and the exponent is increased by 1 every time we move to the left. So 10 to the 0 is the 1's place, 10 to the 1 is the 10's place, 10 to the 2 is the 100's place, and so on. And now in almost the exact same way in binary, our places go up by 1, 2, 4, 8, 16, 32, and so on. And in the binary case, that means that we have a base of 1. So in an op-amp circuit, we need to treat each binary digit according to the weight of its respective position in the binary string. And that's exactly what we do here. As I said, they go up by 1, 2, 4, 8, 16 in that pattern. So in this case, we only have 4 bits. So we just need to go up to 8. Now, let's take a look at an example. And let's say if VREF equals 1.28 volts, what is VO going to be for the given input bit string? And the string we're going to look at is 10, 10. And the switches, by the way, are all lines to represent 10, 10. Now, instead of writing the output equation from scratch, let's just take a look at the equation and work backwards to see where it came from. So the output voltage of this DAC circuit is this. Now, this is a summing amplifier, but one of the key differences here is that the input voltage, which is VREF, is the same for all of our inputs. That's why VREF is distributed to each one of our input terms. Now, each of these terms in parentheses comes from our knowledge part of the summing amplifier, which tells us that the gain applied to each of our inputs is equal to the value of the feedback resistor, which is this Ri resistor over here, over the value of the input resistor, which is all of these resistors right here. Of course, you only look at one at a time. Now, in this case, we make the feedback resistor also equal to Ri, and that's to help facilitate some crossing out in just a second. And to account for whether or not we even apply an input at all, we add in these D0, D1, and D3 terms, which effectively turn our inputs on or off depending on if the bit is 1 or 0. Okay, so now let's do some canceling out. So all our Ri's cancel out, and we're just left with some fractional coefficients for each of our inputs. And we see that V0, which is our least significant bit, because it's our rightmost bit in this string, is multiplied by 1/8, and that makes sense because it is least significant. And D3, our most significant bit, is multiplied by 1. So now let's apply our binary input string 1010 and our reference voltage 1.28 volts. What's going to happen here is you're going to see that V0 and V2 go away because they are 0. And we're left with 1.28 volts times 1.25. And 1.25 is just the sum of 1 plus 1/4. And we see that the output voltage is going to be negative 1.6 volts. And it's negative because this is, again, another application of the inverting amplifier. Now, as a side note, this DAC can produce 16 discrete values between 0 and negative 2.4 volts at 0.1 volt intervals. So that means that every time you add a 1 in binary to the bit string, the output voltage goes up by 0.1 volts. And the maximum voltage we produce is negative 2.4 volts, which happens when we have a string of 1, 1, 1, 1. And the minimum voltage we produce is 0 volts, which happens when we have a string of 0, 0, 0, 0. And so that is digital to analog converters. So that's a contemporary application of the op-amp. So let's go back to the op-amp's origins. One of the initial applications of the operational amplifier was in analog computing. So you might say, analog computing. But yes, op-amps, as we've learned, can be configured to add, subtract, multiply, divide, and even integrate. And these circuit blocks can be connected together to solve complex mathematical problems. So for example, during World War II, if you want to calculate the trajectory of a missile, it required a huge, slow, and unreliable mechanical analog computer, which used spinning wheels and gears and all sorts of stuff like that. But with the op-amp, we could have a faster, cheaper, smaller, and more reliable replacement for the clunking behemoths that were mechanical analog computers. So that was one of the first applications. And on the right is what the first op-amps looked like. So they were not integrated circuits, they were not silicon chips, but these were vacuum tube H outputs. As you can see, you have 2 vacuum tubes on this one. And this was called the K2W, which wasn't the first op-amp, but it was probably the most popular vacuum tube op-amp. So I'm going to try to explain a simplified missile trajectory computer, but that's simulating a real-world system. So nowadays you can use all sorts of computer software to predict how a system is going to behave without actually building it. But back before we had all this computing power, we can model real-world systems using op-amps. So for example, say you are the designer of the suspension system to be used on a military jeep. So here we have a chassis represented by mass M, a spring with spring constant K, and a damper with damping constant V. The ground beneath the wheel changes elevation with time according to x of t. So we want to know with these constants at a given input stimulus, that is x of t, how will the body of the vehicle react, that is y of t. Because ideally we want y of t to move up the body to be 0, or at least very small. So you just try out a bunch of dampers and springs and see what happens, but that's going to waste a lot of time, effort, probably money. So let's model it first. So to do so, the first thing we need to know is the equation of motion for this mass spring, the Atlas system. So let's write that out. And if you ever take control systems course, you'll learn how to derive that equation. But for now, you can take it for granted. And what we do now is convert this equation into its equivalent block diagram representation. And that looks like this. So how does this diagram make any sense? Well, let's go through it quickly. Well, you get an input x of t and an output y of t. If you take the derivative of the output twice, you get y prime of t and y double prime of t. And since we're going from right to left, that corresponds to two integral blocks because the integral of y prime of t is y double prime of t is y prime of t. And the integral of y prime of t is y of t. So that's where that comes from. So now we have y prime of t and y double prime of t available for our use. So we can just grab them and multiply them by whatever constants we have in our system and feed them back to these summing junctions. And these summing junctions accomplish the subtraction we see in the parentheses down here. And this 1 over n block multiplies the whole thing on the outside. So regardless if that makes any sense to you, the real point here is that we have the ability to synthesize each one of these operational blocks using op-amps. So the summing junctions are different amplifiers. The red blocks are our non-inverting and inverting amplifiers. And our integral blocks are, of course, integrators. So when we connect our op-amp blocks up in this way, we can apply input x of t, which might be via a function generator, and we can observe our output visually with an oscilloscope, and we can physically see what the movement of our g-taxi would be. And so there you have it, modeling real-world systems with op-amps. And so that about wraps it up for op-amps. I hope you now have a good understanding as to how op-amps work, the theory behind them, and how you can apply them in the real world. And if you have any questions about this video, please leave them in the comments, and I'll get back to you as soon as I can. And if you have any other feedback, please, I'd love to hear anything you have to say. So thanks again, and I hope you have a wonderful day. Hey, how's it going, everyone? This is the solid state workshop with essential and practical circuit analysis. This is going to be a two-part series on circuit analysis, so with everything you have, let's go. So what exactly is circuit analysis anyway? Well, circuit analysis is a toolkit for understanding and designing more complex circuits. So if you want to get into the world